Welcome to this deep dive where we untack cutting-edge machine learning research for you.
Glad to be here.
Today, we're tackling a really interesting paper. It focuses on a crucial bottleneck in building genuinely smart chatbots and AI assistants.
Right. We're talking about planning ahead in conversations.
Exactly. How do they plan without getting totally bogged down by, the computational cost? If you're curious about how the next generation of conversational AI might actually think before speaking, well, this is definitely for you.
Yeah, you know how those back and forth chats are just key to making these things useful.
Absolutely.
But making sure it's a good conversation, engaging, safe, it's tough. The real quality often only shows up way down the line.
Right. And the obvious first thought might be, well, just have the AI simulate the future conversation turns using its own language model at every step.
Yeah, run the possibilities.
But as this paper really points out, that gets impractical super fast, especially when you want instant responses.
Oh, totally. That's the core insight, yeah. It learns these transitions and rewards directly in the semantic space. And then it uses planning algorithms like Monte Carlo Tree Search
MCTS, right.
to explore possible futures, but incredibly quickly, because it's not calling the big LLM all the time.
How quickly?
Well, they report it's about 70 times faster than the traditional simulation way.
70 times.
Yeah. And importantly, they actually achieve higher rewards, so better conversations, within a practical time budget, like a few seconds per turn.
Wow, okay, that's a potential game changer then. Real-time planning that was maybe out of reach before.
Pretty much. Scope unlocks that.
So the paper mentions two phases. A learning phase where it builds this map and understands the dynamics.
Right, that's done offline once.
And then the runtime phase where it actually uses that map during a live chat.
Exactly.
Okay, maybe we should step back a bit. What's the sort of background that led to needing something like scope?
Good idea. So the authors set the stage by clearly defining this multi-turn conversation planning problem. They really emphasize, the dynamic nature. The fact that a human's response is fundamentally unpredictable, stochastic.
You never know exactly what the user will say next.
Right. And how the AI's current reply can massively shape where the conversation goes later and its eventual quality or success.
It's like chess, but your opponent's moves are a bit random and you only get the score at the very end.
That's a decent analogy, yeah. They frame it formally as a Markov decision process, an MDP.
Okay, MDPs. For listeners maybe less familiar, that's just a mathematical way to model decision-making over time when things are uncertain, right?
Precisely. So in this context, the states are the conversation histories, ever said so far.
Got it. The context.
The actions are the possible responses the LLM could give.
The choices it has.
Then you have a transition function, which is basically the probability of moving to the next state, given the LLM's action. And then crucially, the human's response.
That captures the uncertainty.
And finally, a reward function that scores how good each step or the overall conversation is. Is it engaging? Is it safe? That kind of thing.
But as the paper notes, trying to solve this MDP directly with standard algorithms, it's just impossible.
Completely infeasible. The number of possible conversation states and actions is astronomical, mind-bogglingly huge.
Like mapping every grain of sand, you said earlier.
Yeah, something like that. So because of that complexity, researchers looked at methods like Monte Carlo Tree Search, MCTS.
Which has worked well in other areas like game playing and even some language tasks.
Right. Vanilla MCTS, the standard version, it works by running simulations to explore the possibilities.
Okay.
In conversation planning, traditionally, this meant using another LLM to simulate how a human might respond to different potential AI actions.
Ah, so the planning AI essentially chats with a fake user, an LLM simulating a human to see what happens.
Exactly. It's trying to look ahead, see where different responses might lead. That look ahead is what gives it strategic capability.
Trying to anticipate reactions. Makes sense. But you mentioned the bottleneck.
Yes, the huge, massive bottleneck.
Yeah.
The computational costs of those LLM-driven simulations.
Because each simulation step needs a full LLM query.
Which takes time and compute power. And to plan effectively, you need lots of these simulations.
How many are we talking?
Well, the paper mentions vanilla MCTS needing hundreds, potentially thousands of seconds of planning time per turn to get decent results.
Okay, yeah. That's just not going to work for a real-time chatbot. No way.
Absolutely not. Which brings us right back around to scope.
And its big idea. Do the MCTS, but without those slow LLM simulations.
Precisely. operate entirely within that learned semantic space instead.
Because the meaning, the flow, can be captured by moving around on this semantic map.
That's the key intuition. Scope learns to predict the probabilistic transitions, how a conversation in one meaning area might shift to another given an AI action.
And it also learns the rewards associated with different parts of the map.
Right, so simulating a future path becomes incredibly fast. Instead of generating text, it's just sampling transitions and adding up rewards within its learned semantic model.
That's where the 70x speedup comes from. It's like navigating with a pre-calculated GPS map versus exploring every side street yourself in real time.
Good analogy. And interestingly, the authors connect this to a broader idea that maybe LLMs are better at proposing good actions, while a different mechanism like scope handles the efficient planning and selection.
Okay, interesting paradigm shift there. So let's get into the specifics of scope. How does it actually represent this semantic space?
So they use a semantic embedding model. In their experiments, they actually use the feature layer from LlamaGuard 2.
Okay, so a pre-trained model component.
Right. This model, let's call it F, takes a whole conversation history and maps it to a single point, a dense vector, in this continuous semantic space.
So each point captures the essence of a conversation state.
Exactly. And the potential LLM responses, the actions, are also projected into this space as a MA.
Got it. So states and actions both live on this map.
Yes. And they provide some theory, which is in the appendix, suggesting this transformation preserves the optimal action. Basically, the best thing to do in the complex real world is still the best thing to do on the semantic map, under certain assumptions.
Okay, that's important justification. Now, how does it learn the transitions? You mentioned they're probabilistic because humans are unpredictable.
Right. A simple deterministic neural net wouldn't cut it. You need to model the uncertainty, the randomness.
So what do they use?
They explored a couple of options, primarily mixture density networks, MDNs, and also deep ensembles.
MDNs can output probability distributions, not just single points.
Exactly. These models are trained on a big data set of real conversations. They learn to predict the distribution over possible next semantic states, given the current state, and the semantic action.
So it can sample potential futures.
Precisely. And they actually break down the transition model, TE, into two parts. One predicts the semantic representation of the AI's response itself, and the other predicts the resulting overall conversation state.
Okay. Sort of like predicting the AI's semantic move and then predicting where the whole conversation lands after that move.
Yeah, that's a good way to think about it.
And the rewards. How does it know what's good or bad on this abstract map? It can't directly see, say, the word count of the actual human response while it's simulating in semantic space.
Correct. That's another clever bit. They train a separate reward model, let's call it FR. This model learns to predict the expected cumulative reward associated with just being at a particular point on the semantic map.
Okay, so it predicts the long-term value of a semantic state.
Yes. And then the instantaneous reward for a single transition in the semantic simulation is approximated simply as the change in this predicted value. So FRS.
I see. The reward for taking a step is how much better or worse the predicted future looks from the new spot compared to the old one.
Exactly. And interestingly, they note you might even be able to use the same underlying model for both the semantic embedding F and this reward prediction FR.
Streamlining things further. Okay, so we've got the map, the transition model, the reward model. How does Scope put this all together during a live conversation?
Right, the runtime phase. So you type something. First, the base LLM generates a set of candidate responses, maybe 5 or 10 options.
Okay, proposes some actions.
Then Scope takes the current conversation history in each of those candidate responses and projects them all into the semantic space using the embedding model F.
Puts them on the map.
Yep. Now it kicks off the MCTS planning, but entirely within semantic space. It uses the learned transition model T as its super fast simulator.
Simulating semantic moves, not text.
Right. It rolls out simulations, maybe say 4 steps deep into the future, sampling transitions based on the learned probabilities. For each simulated path, it estimates the total future reward using the reward model R by summing up those instantaneous reward differences.
Accumulating the predicted value.
It does this many, many times, exploring different branches, all within a strict time budget, say 3 seconds. This exploration allows it to update its estimate of the long-term value, the Q value, for each of the initial candidate responses.
So it quickly figures out which opening move seems to lead to the best futures on the map.
Precisely. And after the time is up, it simply picks the candidate LLM response that has the highest estimated Q value.
And sends that one back to the user. It's like this rapid internal simulation tournament before choosing the winner.
That's a great way to put it.
So the experiments, they tested this against various conversation starters?
Yeah, diverse topics from multiple data sets.
Yeah.
They use those two practical reward functions we mentioned. Cumulative length of the human's responses.
As a proxy for engagement.
And cumulative harmfulness score, using Lamagard 2 to rate the conversation's safety.
Both really relevant for real-world systems, and both depend on how the human actually responds, making planning crucial.
Exactly.
And the results. How did scope stack up against simpler methods?
It did very well. Compared to baselines like just picking randomly or greedy approaches that only look one step ahead.
The myopic ones.
Yeah. Scope consistently got higher cumulative rewards for both engagement, response length, and safety, lower harmfulness, especially over longer conversations.
Because it's considering the long-term impact.
Right. And importantly, it also outperformed vanilla MCTS when both were given the same short, realistic planning time.
Because vanilla MCTS just can't simulate very far ahead in, say, 3 seconds due to the slow LLM calls.
Exactly. Its simulations are too slow, so its search is very limited. Scope, being much faster per simulation, can explore much more deeply and effectively within that same time budget.
Makes sense. They mentioned a concrete number for the engagement benefit.
Yeah, figure 3B in the paper suggests, on average, Scope led to humans writing about 150 more tokens over a 5-turn conversation compared to the greedy approach. That's quite a bit more engagement.
Definitely noticeable. And they had visualizations, too.
Yeah, really cool plots showing conversation trajectories in the 2D projection of the semantic space. You can literally see Scope steering the conversation towards regions associated with higher rewards, like longer responses or lower harmfulness, while the simpler methods might wander off and get stuck.
Visual proof of the better navigation.
And again, the headline figure. Scope planned 70 times faster overall than vanilla MCTS while getting these better results. One detail from the appendix is that each individual simulation rollout within the MCTS is actually 92 times faster in scope.
Just emphasizes how much overhead the LLM calls add. Did they do any ablation studies, like changing parts of scope to see what happens?
They did. They compared using mixture density networks versus deep ensembles for the transition Model T.
How did that turn out?
It varied a bit. Deep ensembles seem generally slightly better, particularly for minimizing harmfulness. MDNs were maybe a bit better for maximizing response length sometimes. It suggests the best choice might depend on your specific goal.
Interesting. Not one size fits all.
They also looked at the search depth. D, how many steps ahead Scope simulates in MCTS.
Does deeper always mean better?
Generally, yes, up to a point. Performance tended to improve as they increased depth from 1 to about 4 turns. Going much deeper didn't always help more, and of course cost more time. So looking a few turns ahead seems like a sweet spot.
That makes intuitive sense for conversations. This really does seem like a solid step forward. Scope offers a practical way to get sophisticated long-term planning into real-time conversational AI.
Yeah, by moving the planning away from slow text simulation into this faster semantic realm, it overcomes a major hurdle, definitely promising for building better AI assistants.
And as always, folks, if you want the nitty-gritty details, the link to the paper is in the show notes. Definitely worth a read.
For sure. Significant piece of work in this space.
Okay, now for our favorite part, the novel notions segment. Where could this kind of thinking lead next? I had one idea. Building on this efficient semantic planning. What if we could personalize the semantic space itself?
Ooh, interesting. Personalize the map. How do you mean?
Well, imagine training, or maybe just fine-tuning, the semantic embedding model F, and maybe the transition and reward models too, specifically based on an individual user's past conversations.
Ah, I see. So my semantic map might be slightly different from yours, reflecting how I communicate.
Exactly, with explicit consent and privacy safeguards, of course. But based on your history, the system could learn a more accurate model of how conversations with you tend to flow and what you find engaging or helpful.
That could lead to incredibly tailored interactions. The AI could predict your likely responses or interests much better within its planning. You might need something like meta-learning to adapt quickly with limited user data, perhaps.
Yeah, maybe. The benefit is obvious. A much more personalized, intuitive experience. The AI feels like it gets you better on a deeper level.
But a weird, non-obvious side effect. Could we see the emergence of distinct semantic dialects? If my model is tuned to my specific style and yours to yours, how does that affect the underlying representation? Could AI assistants trained on different people develop slightly different understandings of language?
Oh, semantic dialects. That's a wild thought. Very sci-fi, but grounded in this tech. Okay, another angle. What about integrating external knowledge more deeply within the semantic space?
Expanding the map's domain.
Sort of. Right now, it embeds the conversation history. What if we could also embed relevant documents, maybe facts from a knowledge base or even parts of a user profile into that same semantic space?
So the space represents not just the chat, but the relevant world knowledge too.
Yeah. And the transition model could learn to navigate this richer space. It could learn that moving towards a certain knowledge node on the map is a good strategy in some contexts.
So the AI could proactively introduce relevant facts or steer the conversation based on this broader context without needing slow simulations involving retrieving and processing that external info separately.
That's the idea. Imagine a customer support bot. Its semantic map includes not just the chat history, but also representations of product manuals or FAQs. The planning could naturally lead it to bring up relevant troubleshooting steps.
That could be incredibly powerful for knowledge-intensive tasks, education, research assistance.
The big challenge, though, is how do you effectively mash up these different kinds of information, dialogue, documents, user data into one coherent semantic space? And how do you train the transition model to leverage it all smartly?
Yeah, that's non-trivial. Getting the representations right and making sure the model can actually use the embedded knowledge meaningfully during planning, that's the research frontier. But the potential payoff is huge AI that's not just conversational, but genuinely knowledgeable and context-aware in its planning.
Imagine an AI tutor that anticipates your next question because its semantic map connects your current confusion to related concepts you struggled with earlier.
Yeah, truly proactive assistance. It shifts from reactive answering to more guided interaction.
Well, those are some fascinating possibilities branching out from scope.
It's definitely food for thought. As always, the real future might surprise us.
Indeed. And that's all the time we have for this deep dive. We hope this look at scope and efficient conversation planning sparks some ideas for you.
Hope you found it useful.
Join us next time as we explore another corner of the rapidly evolving world of machine learning.